All right, introducing radians. So first of all, we're going to learn the definition of what a radian is. And so what I have here is a circle with a certain radius, right? I'll draw that radius r. And that radius was based upon this triangle that I'm holding that's a little bent up right now. But what kind of triangle is this? It's an equilateral. What's special about an equilateral triangle? All the sides are the same and all the angles are the same. And what are they equal to? What are all the angles in an equilateral triangle?
60.
They're all 60 because it still has to add up to 180.
Sorry for the interruption. If we can please now have our grade 10s with the last name beginning with letter M through Z, to please quietly proceed to the cafeteria to retrieve their student cards.
Now,
Thank you.
if I took this triangle, and I should get some new cardboard so it's not as bent, and I pushed these sides down, that would bend the third side to make it curved. Can you see that? If I take a triangle, so I have my equilateral triangle, I push down, so now that side is curved. Okay? Since all of these lengths are the same, even though I pushed it down, all of those lengths are still the same. Okay? If you would do that, well, I wanted green, not blue. There we go. If I would do that so that this length is still r and this length is still r, this angle right here is 1 radian. That's the definition of the radian. When the arc length is the same as the radius, you have 1 radian. Does that mean, does 1 radian change if I made a bigger or smaller circle? That's the first question. Well, we would hope not, and actually it does not change no matter how big or how small that circle is. But now we want to try and figure out, if I do this once, how many radians would there be in the whole circle? Based on the picture, if I would estimate doing that same length again, oh, that might be a little bit. How many does it look like fit around the whole circle? 6.5, maybe? So now our question is, how could we find that out exactly? Should we use a number instead of an abstract concept? We're using abstract right now because we're just using r for radius. How many radiuses does it take to go all the way around the outside of a circle? If the radius is 1, okay, what's the distance all the way around? Two pi. If the radius is 1, the distance all the way around would be 2 pi. What is that approximately as a number? 6.28. So here's 1, another 1, 2, 3, 4, 5, 6, and then 0.28 left. That would be measuring using numbers. There would be 6.28 radiuses around the circle. Does that make sense? That if I translate it to this circle, my circumference is 2 pi r. That means that there are 2 pi radiuses that fit around the circle. In fact, that is another way that sometimes circumference, another way that circumference is sometimes put down is pi times the diameter, because 2 radiuses is the diameter. And if you think about a full diameter to here, another full diameter to there, another full diameter to there, you get the idea that there's 3.14 diameters around the circle. With grade 9 students, I used to get them to take different sizes of circles, cut out pieces of string exactly the length, the diameter, and measure how many strings they needed to go all the way around. And it didn't matter what size of circle you have, you will always need 3 and a bit diameters to go all the way around. And then they redid it by cutting radiuses. And they always found they needed 6 and a bit to go around. So the definition of 1 radian is when the arc length is the same as your radius. The next thing we can now state because of this is that there are 2 pi radians in a circle. That's how many radians it would take to go all the way around. Because if we think about the arc length and their circumference, our circumference formula tells us there are 2 pi radiuses around the edge of our circle. And every time we have a radius around the edge of our circle, we have a measurement of 1 radian. Now in this equilateral triangle, right, all the angles are 60 degrees. So if we go back to our picture up here where I drew those equilateral triangles, this angle right here is 60 degrees. As soon as I squish it down to make this bend, what happens to this angle? It gets a little bit smaller. So a little less than 60 degrees. So when we're comparing radians to degrees, well, 1 radian right now, just based on that picture, is a little less than 60 degrees. And if you can imagine this later, it's going to help you remember what a radian is like. So when I asked you to jump up and do 3 radians, that would be a little bit less than 180 degrees. Just a little bit less than 60. Well, let's figure it out exactly. For every circle. Because it wouldn't matter how big or how small you make your circle. And this was one of the things that was a question of mathematicians like thousands of years ago. Archimedes was one of the greatest mathematicians that looked at this. But you see historical documents that would say stuff like, there are 3 diameters in a circle. And then someone would say, no, I took string and I measured it, and that's definitely not accurate enough. And so there became a sort of a puzzle, a mathematician's puzzle back in 300 BC. How do we measure the length of the circle perfectly? How do we figure that out? So here's a little historical lesson, because Archimedes was the first mathematician who said it's an interesting number that we can't say exactly what it is, but I know that I can get to as close to it as possible. And he used something that he called his method of exhaustion. Sounds tiring. So what he did is he started off with a circle like this and said, if I break this into 60-degree angles, that would make a perfect hexagon inside of my circle. And if I was racing someone and I could choose whether I wanted to run around the green track, which is all the way around, or the blue track, I'd pick the blue track because it's shorter.